Hi, good afternoon, everyone. Today we're going to be learning about how we can go about pipelining our beta in order to further increase its performance. Before we get into that, though, let me just remind you a couple things about labs. So the first thing is your unpipelined beta lab is due this Thursday, so hopefully you're all far along in it. Please don't wait till the last moment, as that one can take a while. And the other thing we wanted to mention is that Lab 6, the cache-related lab, has now been posted, and although it's not due until after Quiz 3, we strongly recommend trying to work on it beforehand because it'll help you learn the cache material. Okay, so let's get started. So at this point, you should hopefully be very familiar with this image of the unpipelined single cycle beta, okay? And in lab, you're going ahead and building this. And as far as performance is concerned, we measure performance using this equation, which you've seen before, which is that the amount of time it takes for a program to run is based on three things. One is the instructions per program. We can't really control the number of instructions per program too much. Second is the cycles per instruction. And third is the time it takes to execute one cycle, okay? So the CPI, or cycles per instruction, and T clock are things that, we might be able to do something about. So in our unpipelined beta, we already got to the point where we said, well, let's assume a very simple model where CPI is equal to 1, okay? So without doing much more complicated architectural things, which you won't see in this class at all, you could actually take a graduate level computer architecture class to see how you might lower CPI below 1, but we're going to kind of use that as our limit for 6004. So what we want to do is we want to try to lower T clock. We want to make our cycle time faster. And how do we do that? We do that with our old friend pipelining. Okay, so before we start to pipeline, let's think about, in an unpipelined case, what is our T clock controlled by? So it's controlled by the longest path for any of your instructions. So if we bring up here on the side our beta diagram again, and we think about, okay, well, what is that longest path that I have to allow enough time for in my clock period? If you think about the register to register TPD, you see that you can start off here at your PC. The PC then it becomes the address for your instruction memory. We read from the instruction memory our actual instruction. Then we do some decoding and read from our register file the contents of the registers that we're trying to use as our operands. We then go through our ALU, perform whatever instruction we wanted to execute, and then we write our data back into our register file. So certainly it's the case that T clock needs to be long enough to allow for all of that to happen, okay? In addition, though, we have the second path here in red, which shows a memory access. So it starts off pretty much the same with accessing the PC using, sorry, I think this is a little too close to me. Let's see if that does better. We start off with a PC going through the instruction memory, and in this case, after reading the register file, what happens in the ALU is that it's not producing your actual result, it's producing the address that you want to use in your memory. And so then that address is fed into the data memory, and then we can get a value back from there and then use that to write back to our register file. So that, in fact, turns out to be our longest propagation delay in the beta. And so we need to make sure that our T clock can satisfy that the entire time that it takes to do that. So what does that entail? You can kind of think of your instruction as having to go through various phases of our beta. So you have your fetch portion, which is going through your instruction memory and fetching your instruction. You have your register file portion, which is reading the values of the registers you're using. You have your ALU, which is the time it takes to do your computation. You have your memory, which is the time it takes you to access your memory. And finally, you have your write back, which is the time it takes you to write your result back into your register file. Okay, so our T clock is the sum of all of these pieces. So what we'd like to do is we'd like to say, well, you know, can I make this better, right? Because this is kind of slow. You know, even if I want to look at an operation that might be simple and doesn't even use data memory, I'm still going to be limited by the T clock that does allow for enough time to go through my entire data memory. So what might we be able to do to make this better? So what we were going to try to do today is we're going to try to pipeline this beta. And we're going to divide it into, you know, smaller pipeline stages. And when we, you know, learned about pipelining before, what we saw is that by pipelining, we can make our clock period smaller. As a result of making our clock period smaller, we can hopefully, ultimately, make the performance of our processor better. Now, you could also say, well, you know, if I'm making my processor pipeline, then now I'm taking more cycles in order to execute one instruction. And while that's the case, if we think about the throughput, though, that we're able to produce in a pipeline beta, you're still able to get a throughput of one instruction per cycle. And so effectively, our CPI continues to be 1, yet we're able to reduce T clock significantly, okay? And so what we're going to go through today is what we call a classic 5-stage pipeline. Classic here refers to the pipeline models that were introduced back in the 1980s, and it's what you would see in any introductory computer architecture class. And the 5 stages are as follows. You start with an instruction fetch stage. Okay, the instruction fetch stage is responsible for sending the PC to the instruction memory, fetching the instruction that you're going to execute in that that you're beginning at that cycle, and also updating your PC to point to the next instruction. This information is then passed to the register file stage. In the register file stage, you take the information about that instruction you just fetched, and now you can read the operands that are associated with that instruction. You then take those operands, you pass them on to your next stage, which is your ALU stage. In your ALU stage, you're going to do the computation that you want to do on these operands. Then you pass that onto a memory stage. So if we happen to have a load or a store instruction, then what happens is that the ALU would have computed the address for our load or store, and now in the memory stage, we would actually access our memory, either reading or writing it, depending on what it is we're trying to do. If the instruction is not a load or store, then all that this stage would do would be to pass along the result from the ALU further down the pipe. And finally, we have the write back stage, which writes our results back into our registers. Okay? So if we think about T clock in this scheme, where we have 5 separate stages, what is our T clock going to be? It's now no longer the addition of all of these pieces. Instead, it's just the maximum of them, right? So whichever piece is the slowest is going to control our T clock, but that's certainly going to be better than the sum of all of these 5 things together. Okay, so, well, what's so hard about this? Right? I mean, you could say, well, I already know how to do pipelining. I'll take my my beta, I'll draw my endpoints, I'll draw some contours. I've got here 5 stages, and I'm done. Right? What's wrong? Why can't I do that? Any ideas? The reason we can't do this is because this isn't a combinational circuit. Okay, so what we learned so far is how to pipeline combinational circuits. But here we have 2 things that we need to be aware of. The first is that the beta has state, right? So we have our PC register, we have our register file, we have our memories. All of that is maintaining state. And so this is no longer a combinational circuit that, which is something that we know how to pipeline. In addition, if you look at the way that the data flows through our beta, what you find is that for the most part, data flows from the top here down to the bottom. However, there are a couple paths that don't do this. They actually go in the opposite direction. And so those paths are this one right here, which is our write back into our register file, kind of goes up against the stream of our pipeline direction. And similarly here, the result of updating the PC register is also going in the opposite direction. And so, that's something we don't know how to deal with, right? There's the way we've learned how to pipeline is you can only go in one direction. It doesn't make sense to go against the direction of the pipeline. So we have to deal with that as well. And so today we're going to go through the details of, well, how do I deal with these issues in order to actually create a well-formed pipeline pipeline beta that will execute my instructions correctly. All right, so in order to understand a part of what's difficult about these loops that go back, these loops cause what we call hazards. There are two different types of hazards. One is called a data hazard, and what this refers to is, suppose that I have a pipeline of multiple instructions. And let's say that instruction number 1 is writing to register R2, and instruction number 2 wants to read register R2. Well, if they're both in the pipeline at the same time, then instruction number 1 hasn't yet had a chance to write its results into the register file. And so this is what we call a data hazard, which is where it's not, if you were to read R2 in instruction 2 from the register file, you would be reading the wrong value because it's not the most up-to-date value of R2. Okay, so that's what we're going to learn how to deal with today. The second type of issue, and that has to do with the loop back arrow that we saw going back into the register file. The second place where we went back in our beta architecture has to do with the program counter and changing the sequence of operations to be something other than going to the next instruction. And so for example, suppose that I have a branch instruction. When I put the branch instruction into my pipeline, I don't know right away whether the next instruction that I need to stick into my pipeline is the instruction that's immediately after the branch, or is it the branch target? And so I might make a mistake and as a result have something that I have to fix further down the road. And so this is what we call a control hazard, and that's caused by branches, by jumps, by exceptions, and we're going to get into that in Thursday's lecture. Today, we're just going to focus on data hazards and how do we deal with those. Okay, so what's our plan of attack? We're going to first come up with a 5-stage pipeline that works for instruction sequences that don't have any of these hazards. And then we're going to add mechanisms that can deal with the data hazards today and that can deal with the control hazards on Thursday. Okay, so what we have here is we've redrawn our unpipelined beta data path. And the main thing that we've done to it is that we've stretched it out so that you can kind of see the individual stages of your pipeline going, showing how the data is traversing down through these stages. There are a couple additional changes that we've made. The first is over here, which is that for now, because we're only dealing with data type of hazards, we're not dealing with control at all, we're just assuming for today that our instructions just execute sequentially, okay? And so the only thing we have here as far as hardware is concerned is the PC+4 logic. We don't have the whole mux that can select different inputs for your PC. We will get to that on Thursday. The second thing that's changed here is our register file. What you see is that we've split it up into two. It's still actually just one register file, but we split up its functionality into two. There's the read portion and there's the write portion. So the read portion happens way up here right after we fetch our instruction. The write portion only happens at the very end of our cycle, okay? And so by splitting it up in this way, it makes us not have, oops, sorry about that. Okay, makes us not have these loops that we were worried about. Okay, so now I can go ahead and very easily draw, contours across this and actually create a valid pipeline. Okay, so what do I have here? I have a 5-stage pipeline. The top is my instruction fetch stage. What happens in the instruction fetch stage is you use the PC to look up an instruction in your instruction memory, and you read that instruction out of your instruction memory. You also have the +4 adder, which increments your PC in order to produce the next PC for the next instruction. Okay? In our register file stage, what's going to happen is that we read the registers that the particular instruction that we're interested in, the one that's in that stage of the pipeline, needs to access. The next phase after that is our ALU, and that's where we do the execution of whatever operation it is that we're told to do, using the operands coming from these A and B registers. So note that what we've done here is every place where we've added another pipeline stage, if it crosses part of our data path, then we add a pipeline register. Okay, so these are all the pipeline registers that we had to add to our beta. Then we move on to our memory stage. And what we've done for our memory is, because our slowest piece is always our memory, we actually want to give ourselves an even better chance of reducing T clock by allowing the memory to take 2 of our pipeline stages. And so the way that the memory works is you initiate, excuse me, a load or a store up at the beginning of a memory pipeline stage, but you actually get the result of your read in the next stage. Okay, so we've now turned our data reads to be clocked instead of being combinational. Okay? And then finally we have the write back stage, which is responsible for taking the result, either from memory or from your ALU or from your PC, depending on which instruction it is that you're executing, and writing that result back into your register file. Okay, so we mentioned here that we added a bunch of different pipeline registers. So if you think about what it is that these registers hold, each one of these, sorry about that, each one of these is a different version of a different instruction. Okay, so as we're filling in our pipeline, we're moving instructions down our pipeline, and each one of these instruction registers is going to store a different instruction. So an instruction will start off over here in the IF stage. It's then going to get, on the next clock cycle, it's going to get loaded into this IRRF register, and it's going to be the instruction that's used in order to determine what we do in this stage. At the same time, a new instruction is going to be fetched in our IF stage. Okay? Then we're going to go on to the next cycle. The first instruction is going to move down over here, and the information related to that instruction is going to be in this instruction register. Okay? Our second instruction is now going to have its information in this instruction register, and so on and so forth. So the idea is that each of our instructions in each stage has the information associated with that instruction moving along with it, so that it can at any point in time determine the appropriate control signals that have to do with that instruction. Okay, and so what about our control signals? So the way that the control signals are going to be generated is that you're only going to generate the control signals that are associated with your particular pipeline stage, and they're going to be generated based on the instruction register that's associated with your pipeline stage. So what does that mean? In our register fetch stage, for example, in our register file stage, the control signals that we have to set up are A select, B select, RA2 select, and also we have to create the sign extended constant, which comes directly from our instruction. okay? And so all of that information is going to be created using the instruction that's been put into the IRRF register, okay? When we get to our ALU stage, we're going to take a look at this version of the register, which at that point your instruction would have propagated down to here, and that's going to tell you, well, what should my ALU-FN be? Which, operation is it that this instruction is trying to execute? We then move on to our memory pipeline stage, and there we have to set up our MOE and MWR control signals in order to tell the memory whether we're doing a read or write. And finally, in our write-back stage, we have to tell the register file what it needs to know in order to be able to write, which is we need to set up the control signals WD cell in order to select which of the 3 paths is going to feed the register file, WRF in order to allow a write, and then WA cell to differentiate between regular writes and exceptions. Okay. So in addition, though, to these control signals, aside from just having to split them up into the different pipeline stages, there are also going to be a couple additional control signals that we're going to need to add to our hardware in order to deal with the hazards. So let's take a look at what that might look like. So we're going to start off with a sequence of instructions that doesn't actually exhibit any hazards. And let's just see how this flows through this pipeline beta so far. So the way it works is as follows. We start off over here. Our first instruction, they're color-coded, so it makes it a little easier to see what's going on. And so this is our first load. It's being fetched, and at this point, we have fetched this load R1 for R2 instruction. In our next cycle, this first load moves on to the RF stage, and so now in the RF stage, it's going to read the contents of register R1, and it's going to produce this sign extended constant of the value 4 for this load operation. At the same time, we're going to start loading the blue load, the second load, from our instruction memory. And we're going to produce PC plus 4, which is going to point here, you see this little yellow piece, it's going to be the address for the instruction that's immediately afterwards. And so we're preparing for our sub-instruction next, okay? So then we proceed down one more cycle. Now the subtract comes in, the load moves down, further down, and now we have the execution of this green load, which is basically going to add the contents of R1 plus 4. That's now going to become our address for our load. We then move on to the memory phase, and at this point, we pass that, the value that the ALU computed as our address, and we initiate our memory read. So remember that it's now clocked, and we give ourselves 2 clock cycles. So the data is not going to be available to you in this clock cycle. The data becomes available to you in the write-back stage, okay? And so at this point, we've basically filled our pipeline, and you see that you have 5 different instructions in different stages of execution going through our pipeline. And so the result is that our throughput continues to be that 1 instruction is completed every cycle. Any questions so far? Okay, great. Okay, so instead of drawing these fancy color diagrams, which can be very difficult to do, it's actually a lot easier to see what's going on in our pipeline beta using these pipeline diagrams. We actually saw this back a number of lectures ago when we first introduced pipelining. And the way that we're going to use these pipeline diagrams is as follows. So your rows are basically your pipeline stages, and your columns are your cycles. So if we look here at this sequence of instructions, we start off with the green load. It's in cycle 1, it's in the IF stage. Cycle 2, it's in the RF stage, and so on and so forth until in cycle 5, it makes it to the write-back stage. Then in cycle 2, we begin the blue load. Okay, so it proceeds down these 5 stages, and so you see these diagonal paths down our pipeline diagrams indicating the execution of each instruction as it passes through the different stages of our pipeline. So far, this works great, right? And what's going to happen here is that each instruction is going to, so this first load is going to finish execution here after 5 cycles, the second load is going to finish execution after 6 cycles, and so on and so forth. Okay, now based on where we put our register file, we can answer this question of when is it that reads and writes happen. And so the reads happen during our register file stage. Okay, we're going to do any read from register at the point that the particular instruction is in the RF stage. So for example, for the load here, we're reading the contents of register R1, and that's going to be used for our address calculation. Similarly, in our subtract here, we're going to read the contents of R6 and R7, and those will be our operands for our subtract operation. Our writes, however, don't happen until at the very end of the write back stage, okay? And so this is where our hazards are going to come in. So if we look at this instruction sequence, until now we've been dealing with an instruction sequence that didn't have any dependencies. So it didn't have any of these hazards, which is why everything worked so nicely so far. Now we're going to change things a little bit. So if I use my pipeline diagram and I try to fill it with this sequence of instructions, and I try to now analyze whether or not this is going to produce what I want, what you're going to find is, well, I have a problem here. Right? Because add C here is writing to register R2, and this sub C is trying to read the value of register R2, right? Now, when sub C is in its when sub C is in the RF stage, this happens in cycle 3, okay? The add C instruction has not yet written the result into the register R2. And so what would we be reading over here? We'd be reading some kind of stale value of R2, which isn't what we want. So clearly we need to figure out a mechanism to fix this, because our pipeline processor does have to at least produce the results that we expect it to produce. Okay, so we have this data hazard. How are we going to go about solving it? So there are a few possibilities. The most simple one is to say, well, if you have a data hazard, then you need to stall, okay? So what does that mean? It means that you don't allow any new instructions to enter your pipeline, and you start to waste cycles in your pipeline until until that instruction that you're depending on completes its write back stage, and then you can let your pipeline continue. So what does that look like? We'll get into first our strategies, and then we'll get into what they look like. The second strategy is what's called bypass. And the way this works is, well, the idea is that even though my previous instruction doesn't write its result into the register file until after at the very end of the write back stage, that doesn't mean that I don't actually have the result of that execution earlier on, right? If I'm just doing an ALU operation, then by the end of the ALU cycle, I already have that result that's eventually going to be written back into the register file. So if I had some way of passing that data through my data path so that I had access to it somehow, then I could deal with this data hazard. And so that's the idea of bypassing, is that you're passing information earlier than you would otherwise get it. And finally, there's a third strategy, which is speculating. So the idea with speculating is that you're going to make a guess for anything that you don't know. So clearly for ALU instructions, this isn't going to work very well, right? We're not going to be able to guess what the answer of our ALU operation is going to be. But for branch instructions, it turns out that, well, this works really well, right? In branch instructions, we just have one of two choices. We're either going to take the branch or not take the branch. And so it actually turns out that you can build branch prediction logic, which does very, very well in figuring out, or at least guessing, which way that branch is going to go, whether you're going to take it or not. And as a result, use that logic in order to determine how to fill your pipeline. Okay, so we're going to start with strategy 1, which is stalling. Okay, so we have the same sequence of instructions here where we have the data hazard between the add C and the sub C instruction. And so the way that our pipeline is going to look is that basically when the sub C instruction enters its RF stage, meaning it now wants to read the value of R2, you need to have somehow a way of detecting, oh, you know, another instruction that's further down in my pipeline is ultimately going to write to R2, and so I have a data hazard. So what I need to do in that situation is I introduce a stall. And what does it mean to stall? It means that the instruction stays in my RF stage, and all instructions before it also stay in their current stage. So the multiply here is going to remain in the IF stage for multiple cycles. The sub C is going to remain in the RF stage for multiple cycles. Okay? And then what happens to these holes here in the middle, or another term for these is what we call bubbles. They're bubbles in our pipeline. What we have to do is we have to insert what's called a no-op. No-op stands for no operation. So it's basically an operation that doesn't do anything. And there are lots of operations like that. Like for example, if you execute add R31, 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 that's effectively a no-op. And so there is no harm done. Nothing it's not going to change the ultimate effect of anything you're trying to do in your program. And as far as the number of these stalls that we need to introduce, well, there's 3 of them, right? Because the add C is going to write back its data over here at the end of cycle 5. And so that means that in cycle 6, the sub C is going to be able to read its data. But before that, you just have to stall. So, well, this is nice and elegant. You know, it's very simple. It solves our problem of making sure that our pipeline beta does the right thing. But what's the problem with it? It's slow. It's wasteful, right? So we're wasting lots of cycles doing nothing. And so what does that actually do? It actually increases our cycles per instruction. And so this kind of goes against the whole point of why we started today's lecture, which is that we're trying to improve performance. Right? It's not really going to help us very much to make T clock lower if CPI goes up by too much. Okay, so keeping that in mind, let's still think about, you know, how we could go about implementing this stall logic. And it turns out that it's really quite simple. You basically introduce a new control signal called stall, and stall is equal to 1. Basically what it does is it disables things from progressing further down your pipe. And so basically it stops, it doesn't allow the enable for this register or for this and this register, and which basically means that whatever was there is going to remain there until this stall is no longer equal to 1. And how do you determine, you know, whether stall is equal to 1? Well, you have control logic that sets it to 1 based on taking a look at what's going on further down in your pipeline. Okay, so if you have in your RF stage an instruction which needs to read a register that matches the destination register of an instruction that's further down in our pipe, then that means that we have a data hazard, and so we want to set stall to 1. And every cycle, we just keep checking this. And so as the other instructions progress down and out of our pipe, eventually we're going to get to the state where this condition is no longer met. And so at that point, our stall is going to stop being 1, and we're going to let our instruction, which was waiting for a particular piece of data, to now proceed through our pipeline. Okay? Pretty easy. The only other thing to note here is, of course, we probably want to have some special logic for R31 saying that, you know, if the data hazard is because we're reading and writing register R31, there's really no need to stall because we know R31 is just 0. Okay, what about loads and stores? So in this example here, I'm doing a store followed by a load, and the registers that I'm using are completely different. So do I have any kind of a data hazard here? Or could I have any data hazard, I should say? So what happens if the contents of register R2 plus 8, which is the address to where I'm storing a value, happens to be the same as the address of the contents of R3 plus 4, okay? And so now I'm storing something into the same location that I'm trying to read it from, okay? That's a data hazard, just like we had with our register file, okay? In this instance, we're not going to actually worry about building the additional hardware for that. We're just going to assume that our memory itself has the additional logic, just like what we're adding in the rest of our data path to deal with the register file kind of stuff and checking when it is that you need to stall or bypass. The same kind of logic can be added within our memory unit. And so you can assume that your memory unit can deal with data hazards of that sort, okay? Okay, so let's move on to bypassing. So how does bypassing work? We're back to the same sequence of instructions. Again, we have this data hazard between R2 and R5, okay? But now we're saying we don't want to do these stalls, okay? We want to, you know, somehow properly fill in our entire pipeline and make use of it effectively. Well, you know, how can we do that, right? We still have the situation where this add C is writing to R2 at the end of cycle 5, but the sub C is trying to read it in cycle 3. Well, as we mentioned, the data is available to you elsewhere. And so we can just send the data from where it's available to where we need it. And so what this red arrow here is showing us is that I can add a wire that takes the output of my ALU stage and feeds one of the possible inputs for my RF stage, okay? And it's saying that I can read my register not only from the register file, but also one other possibility is that I could take the input of what was just produced in my ALU stage, okay? I can do the same kind of thing with the memory and write-back stages. And so what ends up happening is I have hardware that now looks like this. So what did we add here? We added these two large muxes on the output of our register file, okay? And so we're going to have control signals that we need to generate, which are going to tell us, okay, if there is no data hazard, then just read your register directly from the register file. If there is a data hazard, then determine, you know, whether you want to read this blue, green, or yellow line, depending on where that piece of data is available to you. Okay? So determining, you know, whether or not we're going to use one of these bypass paths is using that same logic that we had for the stall, which is that if the destination register of my ALU memory or write-back happens to be the same as one of my source registers in my RF stage, then that means that I want to actually use a bypass path. Again, for R31, we can special case it so that, you know, we don't actually use a bypass path in that situation. And there's one other question which we need to ask ourselves, which is what happens if we have multiple of these matches, right? So let's say that I have an instruction in the ALU stage that's writing to register R2, and I have another instruction in the write-back stage that's writing to register R2, and I have an instruction in my RF stage that's trying to read register R2. Well, which one should I use? Any ideas? Yep. The latest one. And so where is the latest one going to be located? It's going to be further up in my pipeline. It hasn't gone down as far. So if I have something in the ALU and the write-back stage, I'm going to pick the ALU bypass path in order to make that be the source of the register I'm trying to read. Okay, so what does our hardware look like now? Well, instead of drawing a million wires, we're now labeling these wires called AB bypass. And so what this means is that there's wires coming from here into these muxes, which allow you to select different inputs for your A select or B select inputs. Okay? And so we're going to have to generate the appropriate control logic that's going to say, well, which of these inputs is the right one that we want to get in order to have the right value end up in A and B. Now, note that in addition to grabbing data from the ALU memory and write back along this path, it's also possible that the data that we're going to write into the register file is the PC+4 value. So in addition, we need bypass paths from over here and from over here. Okay? So, as you can imagine, adding all of these wires and these humongous, multiplexers and generating the logic to determine which of the inputs to the multiplexer I should use can get really expensive. Okay, so we found a solution here that works, but it's expensive. And so what is that cost, going to mean to me? It's going to potentially mean that my cycle time actually goes up rather than down. Right? So we have to be very careful about how much bypassing we add. And there's no reason that you have to add what's called full bypassing, which is every single one of these paths. It might turn out, that you run some benchmarks and that you find that really, the thing that's the most useful to you is to only have bypassing from your ALU instruction, because it's more likely that is the instruction, immediately before that you have your data hazard with. In which case, your cycle time might potentially not increase quite as much, but but you'd still have the benefit of having a bypass path in the most common case. And then you still have your stall logic, and so in the case where, let's say you didn't want to add the hardware, then you would stall the instruction, and so you'd take the hit in terms of number of cycles that you're taking to execute a particular instruction. So, these are always trade-offs that we need to consider. Okay, so we're almost there, but let's think about what happens if I have a fully bypassed pipeline. Is there a situation where I might still need to stall? Can anyone think of one? So let's take a look at this example, okay? Suppose that I have my load is writing to register R2. Oops, sorry about that. And my subtract is trying to read from register R2, okay? Well, let's take a look at what the timing of that looks like, even if I have full bypassing hardware, okay? So my load starts over here, and the data that is going to be put into R2 isn't actually available earlier on, because this isn't an ALU operation where, by the ALU stage, I already have my answer. In this case, my data is not available to me until cycle 5. So what do we have to do with this sub C instruction? Even though we have full bypassing, I still have to introduce stalls, okay? So I put stalls into my pipeline, and that keeps my sub C in my RF stage until the data for the load actually does become available to me. And now notice that I actually still am making use of one of my bypass paths, because if I didn't, then I wouldn't be able to read the sub C instructions till cycle 6, okay? So I'm only inserting 2 no-ops in order to deal with the fact that I'm waiting for the data from the load to be available to the bypass path, and then I can make it available to my sub C at the end of cycle 5. Any questions about that? Okay, so the point is that in addition to, even if you have full bypass logic, there are still situations which might force you to also use stall logic. Okay, so let's summarize what we have so far. So strategy 1 was stalls. Basically, it just says, stall the pipeline, don't let anything go through until you create the data that you need, and only then let things progress. And we saw that it was great from a simplistic perspective. It was very easy to build, but it wasted lots of cycles and so made our CPI higher. Our second strategy, which was the bypassing, is much more expensive in terms of hardware, many, many, many more wires. And now you have to start thinking about the trade-offs of, is this complexity of my hardware actually improving my T clock ultimately or not? And so you have to pick the right kind of configuration to get the best performance that you can. Now, is it the case that we can only have 5 pipeline stages? The answer to that is no. And in modern processors, you'll actually find that there are around 20 pipeline stages. And so, of course, the more pipeline stages we add to a processor, the more frequent it is going to be that we're going to have data hazards and the more control logic we're going to need in order to deal with that. And so if you think about, what modern processors have to deal with, there's a lot of logic that has to go into there, and we have to make it very fast in order to allow ourselves to make use of those 20 pipeline stages. Okay, now, so far we've talked about what it is that our hardware can do to deal with these kinds of hazards. But can we do anything in software? And the answer to that is yes. Suppose that I look at this sequence of instructions here, once again, and my load is trying to write to register R2, my subtract is trying to read from register R2. But we know that, with a load, you're going to have to install these 2 stall cycles before you can execute the subtract. So if I look at the behavior of this situation here, I have 2 stalls, assuming that I have full bypass logic. But suppose that my compilers came and realized, hey, there's really no dependency on the multiply or the XOR operation and the subtract. So I could actually reorder these operations and have my subtract occur after those, right? And so I can make my code look like this. And now the dependency of R2 has already 2 filled locations with real instructions, and so I no longer need to insert these no-ops, okay? And so the result here is that I have no stalls, and I've actually been able to fully utilize my pipeline, even though I had this data hazard that had to do with a load, which normally causes me a problem. So that's certainly great, and it works. The main issue with this is obviously, in order for this to help, you have to have data that you have to have other instructions that are independent that you can move around. And so there's only so much that compilers can actually do for you, because more often than not, there actually are dependencies between the instructions. Okay, now let's consider one last solution. Suppose that instead of doing, compiler work or changing my hardware, I said, well, let me take the easy route, and I'm going to change my instruction set architecture so that I define that registers are only updated with a 3 instruction delay. So this becomes part of the definition of my architecture. Is that a good solution? Yes? Why? You're shaking your head now. It's actually an awful solution. So let's go through why, okay? First thing is, compiler writers are going to hate you for doing this, okay? It's extremely complicated to figure out exactly what's being written to when you have to, constantly be calculating what's 3 instructions, that the value is only making it into the register 3 instructions later. Same thing goes for programming. Your programs are not going to be easy to read, very easy to make mistakes. It's just going to be one big mess. And what's even worse is, more likely than not, at some point in the future, you're going to decide, you know what? I don't want to have just a 5-stage pipeline. I want to have an 8-stage pipeline. And now what happens? Even my new definition of my ISA breaks. So the key to remember from all this is that we never want to do this, okay? Instruction set architectures outlive their implementations, and so that is never the solution, okay? So we want to use our hardware solution, and we can use our compilers. This is a no-no. All right, so that's it for today. Next time we're going to learn how to deal with control hazards in our pipeline beta.